Right, just like last week, this week we are primarily going to be doing project work in class. And before that, I'm going to just spend a little bit time telling you what is part 3 about. So part 3 is really, for me, the most interesting part of the project is you're actually starting to design the wing itself. All right, so the objective is still the same as part 2. You are trying to minimize the total mass of the towing airplanes along the 3,000-mile route. So we are fixing a lot of things from part 2. So we are fixing the fuselage, which means we are fixing the ratio of the mass of the fuselage relative to the wing area. Okay. We are also fixing the engine, basically again power to wing area ratio. We are fixing the climb and cruise speeds. And we're also fixing the wing loading. That is basically the wing area to the mass of the entire airplane. Right? So basically this is saying we are fixing the mass of the fuselage relative to the entire airplane. Right? Okay. And we're also fixing the aspect ratio. So the squared span divided by the wing area comes from our optimized result from part 2. Also, let's fix the sweep for now. So what are we designing? We are designing really the taper, twist, and the airfoil shapes. All right. So as you can see, there is a lot of design considerations you can think about when you are changing this. So taper, for example, right, actually changes the volume of how much batteries you can fit into the wing. If you have a rectangular wing, all the cross sections are exactly the same. But if you have a tapered wing, for example, if your root chord is a lot longer than your tip chord, you actually get something more like a conic shape, right? That could potentially fit in more batteries than a straight rectangular wing. Considering that a higher lift coefficient in the center and the lower coefficient towards the tip is also aerodynamically more efficient from a induced drag point of view, right? This might be beneficial. I mean, this is the original 737 design anyway, so you might want to start from the taper ratio of the 737 wing and see if you can change it to make it even better. Okay, so this is basically saying that taper affects the distribution of the lift in a multiplicative way. If you increase the chord length locally of a particular cross section, it increases the lift coefficient proportionally, right? If you double the chord length, it doubles the lift coefficient at both the angle of attack you use for climb and the angle of attack you use for cruise. Right, so there are really two flight conditions you want to consider. One is climb, because that affects how much energy is left when you start the cruising phase, and the one is the cruise that determines how fast you are burning the remaining energy. All right. Twist is another thing that changes the distribution of lift, but in a different way. It changes the lift in a, what I call additive way. So if you increase the angle of attack locally of just a certain cross section, right, it adds something to the lift coefficient. So when you change the angle of attack of the whole airplane, the change in twist actually modifies the distribution of lift in a different way compared to the taper. So these are two independent design variables. When you start to consider, I have to fly at two conditions, one cruise, one climb. All right, so these are important when you're considering multiple flight conditions. So when you're designing the twist, one thing that is a very convenient is that if you want to have different people designing the twist and designing the airfoil shapes, you really want to design what we call the aerodynamic twist. So what is aerodynamic twist? It is not the angle between the root chord and, for example, the tip chord. It is the relative angle between the zero lift angle of the root chord and the zero lift angle of the tip chord. So why do we do that? We do that because whatever design decisions we make on the twist, I mean, if we use just the nominal twist, right, the twist of the airfoil itself, that twist would be invalidated if somebody else changes the shape of the airfoil, right? So let's say if your original airfoil has a zero lift coefficient at 0 degrees angle of attack, and somebody changes the airfoil to make the lift coefficient equal to 0.5 at 0 degrees angle of attack, then you have to change your twist according to it, right? So, but if you use the aerodynamic twist, that decision stays fixed no matter how the airfoil shape would be changed. So that's something I recommend you to do, start from the beginning. Finally, airfoil shapes are something very interesting to design. So you can either you can start from the knockout airfoils, but I would recommend you to actually use the functionalities of X-foil and change the airfoil shapes yourself. Okay, particularly because the airfoil shapes affects the volume of the batteries. You really want to make it thicker to fit in more batteries. However, making it thicker is going to affect other stuff. For example, parasite drag. As we are making the airfoil thicker, we can no longer assume that the parasite drag can just be given by the total exposed area times whatever skin friction coefficient. Why is that the case? If you have a very thick airfoil, why cannot just estimate the parasite drag by the total exposed area? Any thoughts? Yeah, I can right, that's right. The wing is no longer flat, right? But a thicker airfoil, rather than having drag coming from skin friction, it might also have drag from what?
Shocks.
Yes, shocks is one of the potential contributor of parasite drag when you have a very thick airfoil, right? Because for the air to get around the thick airfoil, it has to accelerate to higher speed, potentially greater than Mach 1. Other than shock, what other things can increase when you have a thicker and thicker airfoil?
Form drag?
What?
Form drag?
Form drag, right? From actually flow separation, right? If you have a very thick airfoil, you would, again, the flow has to accelerate more and it has to decelerate towards the trailing edge. So the deceleration introduces adverse pressure gradient, right? That causes flow separation. So your parasite drag actually doesn't just coming from skin friction anymore. So I would recommend use X-foil to estimate the parasite drag of the airfoil you are designing. The only problem is that X-foil doesn't give you any wave drags, right, of shock waves. So again, like remember, we want to design the airplane so that the shock wave drags does not contribute very little to the overall drag, right? Otherwise, it's actually much less efficient. So recommend the estimate transonic effects using Flow 360. And one thing qualitatively you want to make sure is that if you have shock waves, make sure the shock strength is less than Mach 1.1, right? I mean, what does that mean? Remember when we talk about oblique shocks, right? We said oblique shocks are normal shocks. They are just normal shocks at a different frame of reference. So you really not want to look at the Mach number relative to the airplane before the shock. You want to look at the Mach number in the normal direction of the shock wave. You want to make sure that is less than Mach 1.1. All right. the Mach number relative to the airplane may be 1.2, 1.3, right? But like if you multiply by the cosine of the angle of the shock wave, you should get something less than 1.1. Then in that scenario, the wave drag should be pretty much negligible. Otherwise, you may have a significant contribution from the shock waves. Okay, and finally, the total drag computed from flow 360 should be roughly equal to the induced drag you estimate from AVL plus the parasite drag computed from X-foil, right? So doing CFD, it should be a final check on your optimized result. And during the process, you should be estimating the induced drag from AVL and parasite drag from X-foil. All right. Okay. Any questions? The parasite drag from other components like fuselage, engine, and the tail are still using the same old formula. But because we're making the wing much thicker, we need an updated evaluation for its drag. All right. Questions? Okay, if no, let's start working on project. If you haven't finished last week, then work on last week. And if you have spare personnel to start looking at the wing design, I encourage you to do that. What happened? Okay.
That was ridiculous. Oh my goodness. Oh, what you put it so good. I don't really care for where you're going, but I still would prefer permission. I only bought Japan because I said that I thought they were. Otherwise, I'm cool. I'm so sad though, because like my boy super stitches in the starting.